Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. In this video, we're going to tackle topic 7.3, justifying a claim about a population mean based on a confidence interval. So in 7.2, we learned how to construct a confidence interval. Now we're going to dive into some of the more finer details. We're actually going to talk about 4 details. Now, I know the name of this video is justifying a claim about a population mean, but that's actually only one of the 4 details I want to talk about in this video. First, I want to talk about what we truly mean when we say that we are C% confident, for example, 95% confident. I want to talk about what controls the width of an interval. I want to talk about how big of a sample do we need to achieve a given margin of error. And then lastly, we're going to talk about how intervals can be used to justify a claim about a population mean. First, let's remind you what a C% confidence means. So, for example, a very common level of confidence is 95%. So let's start there. Now remember, the whole point is that we're referencing a sampling distribution. Even if it's a T model, it's still pretty normal-ish. But that sampling distribution we are very blind on, meaning that we don't know what the center is. We don't even really know what the standard deviation is. We only are replacing it with S. So we're actually, not only do we not know the mean, but we have to use standard error to find how much we go up and down by, and that's using our sample standard deviation. That's the whole reason why we have to use the T model. But regardless, the idea is that we don't know any of the numbers on the bottom. All we have is our sample. And the idea is this. This sampling distribution is filled with many, many, many samples. So imagine if we were to repeatedly sample from the same population with samples of the same size. Each sample mean found would create its own interval. So this sampling distribution is filled with probably millions of means, different sample means from different samples. So the idea is maybe my sample mean falls right here. Well, if I build an interval around it, then I'm going to capture the truth. And in fact, any sample that is in the middle, 95%, will create an interval that contains the truth. Even if I have a sample that's, right on the edge, pretty high, but still within that middle 95%, well then, hey, I still catch the mean. Even though I barely caught it, I still caught it. So the idea is that when we talk about 95%, we're talking about 95% of samples. And of all of those possible samples, each one of them produces its own interval. So really we're talking about 95% of confidence intervals. And we know that since 95% of samples are near the mean in the middle, then that means that 95% of intervals will contain the true mean. We just hope ours is one of them. So what does an interval tell us? At the end of a problem, the population mean is either in our interval or it's not. Because each interval is based on data from a random sample, which varies from sample to sample. So it's not about a probability. It's not about a chance. It's not about, is it in there? Is it not? A lot of people want to think that 95% is a probability. There's a 95% probability that it's in there. No, it's actually 0 or 1. It's either 100% it's in there or 0% it's in there. So what the confidence is all about, it's all about that sampling distribution. It's all about taking a look at that sampling distribution, even if it's a T model, that's fine, and understanding that most samples are in that middle 95%. So any one of those samples, if found, would build an interval that contains the true population mean. Obviously that means, that 5% will not, but what are you going to do? We're really focusing on the confidence that we truly believe that most samples are in the middle anyway, so ours is going to be one of them. All right, let's look at our battery life problem from the previous lesson one more time. Remember, we were trying to find the average amount of time, the mean amount of time that a AAA battery lasts. So we had our sample mean of 348.7, and we don't know, maybe that's too high, because we don't know what the mean is. Could be above it, could be below it, who knows. And then we take our margin of error, and our margin of error tells us how much we go up and how much we go down. It was about 8.5 minutes, and we got this interval. So what does this interval mean? This is a 99% confidence interval. But what does it mean? Okay, well, first, it means I'm 99% confident that the population mean time that a name brand battery lasts in this given flashlight is between 340.13 minutes and 357.27 minutes. I mean, that's our conclusion, right? That's the simple conclusion. Hey, what does my interval tell me? I'm 99% confident is that the true mean is in that interval. Now, remember, the true mean is either in the interval or it's not. But I know that 99% of all other possible intervals found from the many possible sample means will contain the population mean. So no wonder I'm so confident. There's millions of samples out there, and every sample mean will create its own confidence interval. And I know that 99% of all those confidence intervals are going to contain the true mean. So again, I'm pretty confident that my interval is one of the ones that contains the true population mean. Now, let's play devil's advocate for just a second. If the true population mean is below my interval, that would mean that my sample was so significantly high that my interval did not catch it. This is actually best seen with the picture. So if I think about my sampling distribution, right smack dab in the middle is the mean that I don't know. If the true mean is below my interval, if it is, the only way that could happen is if my sample mean was one of these extremely high ones that when I built my interval, notice I didn't capture the truth. Or it could mean that if the true mean was above my interval, then it means that I must have had one of those crazy low samples that when I built the interval, I missed the truth. But again, that's only if the truth is not in my interval. At the end of the day, I'm never going to know, is it in there or it's not. But remember, I'm trying to get you to understand what these intervals tell us. And the first thing they tell us is where we truly believe with a lot of confidence the true population mean is. But there is this understanding that if the true mean was outside of our interval, then we must have been one of those crazy, weird, significant samples. And the idea is, I just don't believe that I am one of those samples. All right, next up, we're going to talk about the interval width. Please make sure you understand that the width of an interval is basically the margin of error, because you always start off with your mean and you go up and you go down by your margin of error. A sample mean is a point estimate. It's just one value. So the width of your interval is how much you plan on going up and down. So it's actually two margins of error. One is up, one is down. So the margin of error is basically controlling the width. And simply put, more confidence means a wider interval. The more confident you are, the wider your interval will be. Understand that with more confidence, you are pushing out what you believe to be significance or unlikely. You're pushing that to the outsides. For example, with 90% confident, that means that the outside 5%, 5 at the top, 5 at the bottom, there's my 10% that are significant, are what I deem to be significant. So that outside 10%, 5 and 5 is what I deem to be significant. And then again, if I switch to a 99% confidence interval, now I'm pushing further out. Now that outside 1% significant is split up 0.5% at the top, 0.5% at the bottom. So I had to go wider. So all other things the same, a 99% confidence interval is wider than a 90% confidence interval. To better understand this, think about this for a second. If I'm trying to estimate a population mean, for example, the mean amount of time high school students study each night, I could go super wide and say something like this. I'm 100% confident that the mean amount of time students study each night is between 0 minutes and 1 million minutes. To be honest, I bet that I'm correct by that statement. I bet I'm 100% correct that my statement's true. But come on. What would be the point in having such high confidence, but absolutely no accuracy, 0 to 1 million minutes? That doesn't specify or limit me or tighten me to anything specific. That's just terrible. Another example is that I could go super narrow. I could say, hey, I'm 20% confident that the mean amount of time students study every night is between 22 and 23 minutes. Okay, now that's a super tight specific interval, but I'm not confident at all that the truth is in there. Yeah, it's a nice tight interval, but there's no confidence. So I have high accuracy because I have a small tight window, but I have low confidence. So I want the best of both worlds. I want to be very confident and I want a small interval that's accurate. To achieve this lofty goal, I simply need a bigger sample size. That's it. Why? Because bigger samples vary less and should produce a sample mean that is closer to the population mean. So a bigger sample with high confidence will achieve a narrow interval that we could be very accurate. And again, think about this, guys, right? Look where sample size is. It's in the denominator. It's in the denominator. So when you divide by a bigger and bigger and bigger number, that makes the overall value smaller, producing a smaller margin of error. Smaller margin of error means a more narrow interval. So again, the only thing to understand is it's inside of a square root. So let's just say I go from a sample size of 100 to 400. If I times that by 4, remember, timesing by 4, it's actually in a square root, so that's actually reducing me by a half, right? Because the square root of 4 is 2. So make sure that that makes sense as well. So, if you quadruple, that's actually going to cut you in half. Again, because, the difference between 100 and a 4 is timesing by 4. And that 4 in a square root is really a 2. So again, that'll cut you in half. But, the other idea, and I don't want to gloss over this, the idea is if you want your margin of error to get smaller, you can make your T star smaller. A smaller T star comes from less confidence. So I could always be, 60% confident. 60% confidence is going to be a smaller T star. Smaller T star is going to make my margin of error smaller. But I don't want to be less confident. I want to maintain a high level of confidence and still have a small interval. The only way to achieve that is with a bigger sample size. And there's actually one more variable in play here, and that's S. If your standard deviation of your sample is smaller, if your sample in of itself is more accurate, then that will also help create a margin of error that is more accurate and smaller. But, you can't really control that. Like, the standard deviation is what it is. You can't make it whatever you want it to make it. It's just a number, right? So the only thing you do have full control over is the sample size. And I'm going to tell you right now, bigger samples are going to be better. They'll make a smaller margin of error. All right, so this leads us perfectly into the next topic. How big of a sample do we need? Oftentimes, researchers will first determine the margin of error they wish to achieve, and then determine what sample size they need to achieve that margin of error. So this is a little bit weird, but it actually makes sense because, if I'm trying to estimate something and I say, I'm trying to estimate the time that kids study every night, and I want to be pretty accurate. I want to be only 5 minutes margin of error. That means plus 5 minutes, minus 5 minutes. That's 10-minute wide interval. That would be pretty accurate. But what sample size would I need to achieve that? So, I could say that I want a 5-minute margin of error, but then I got to solve for what sample size will produce that. But there's actually lots of issues to do this. So let's walk through those issues one at a time. If I know the margin of error and I'm solving for my sample size, then I do need to know T star. Excuse me. But that's a problem. Because remember how to get T star. T star, we need to know our level of confidence. Okay, so maybe we know our level of confidence, 95%. That puts 0.025 on that bottom tail. But to find T star, I also need my degrees of freedom. But I can't find degrees of freedom because degrees of freedom is your sample size minus 1. And I don't even know my sample size yet. Remember, I'm solving for my sample size. So I actually can't use T star. And we'll talk about how we could adjust for that in a minute. The other thing is S. What do I use for my sample standard deviation? I don't even have a sample yet. I don't even know what my sample size is yet. I haven't even collected any data yet. So I can't put anything into my calculator to get S. So I can't find S either. So how the heck am I going to do this? Well, here's what we're going to do. First and foremost, since you're right, it's impossible to find T star, we could replace it with the Z star. Now, it's not going to be as accurate as we talked about, but it will work. So if you want to be 95% confidence, you are absolutely correct. There's no way you could get a T star because you also need the degrees of freedom, which is based on your sample size. So I could revert back and just use the Z star. It's not going to be the end of the world. It's still going to give me a somewhat decent approximation. Now, the other thing is S. I need to know a standard deviation. So in any problem that's going to ask you to solve for sample size, you will have to be given a standard deviation. Maybe it's a standard deviation from a previous sample, or you're given some information about what that standard deviation could be, because otherwise you can't solve the equation. So these problems are a little bit weird, but let me demonstrate one so you can see exactly what it would look like. And they're actually not that bad to solve. All right, Marcus wants to estimate the population mean circumference of his spherical marbles that his company produces. So his company has these spherical marbles, and he wants to estimate the mean circumference of them. All right, so he wants to do this with a 95% confidence interval, and he wants a margin of error of only 2.4 centimeters. So I don't know how big or small these marbles are, but he wants a margin of error of 2.4 centimeters. It is what it is. I can't change what he wants. So he wants his interval to go up 2.4, down 2.4, which would be 4.8 centimeters wide. What sample size will he need to achieve this goal? All right, so if I'm thinking about trying to answer this question, I'm going to use the margin of error formula. Okay, I don't even know what X bar is, so there's no point in using the confidence interval formula. I'm just going to stick with the back part, the margin of error. All right, he wants a 2.4 margin of error. Now, because I don't know my sample size, I cannot calculate a Z star, so I'm just going to have to, the T star, excuse me, can't calculate the T star. I'm going to have to use a Z star for 95% confidence, and the Z star for 95% confidence is 1.96. It's the best I could do. I mean, what else are we going to do? We can't find a T star. It's just not going to work. All right. The other thing is I'm going to need something to put for the standard deviation. Well, if we keep reading, it does tell us past samples have shown a standard deviation of 0.17. So I'm not saying that this is going to be true for my sample, but past samples have shown that standard deviation, so I guess I'm going to have to use it. So these questions are a little bit tricky, so just pay attention that the margin of error is going to be given to you and the level of confidence will be given to you. For the level of confidence, we're just going to have to use a Z star. Sorry, what else are we going to do? And then for the standard deviation, the problem is going to have to give you something. Remember, when we were working with proportions, we had a similar problem where we just said, well, we don't know what p hat is, so let's just use 0.5 and 0.5. Here, we can't do that. So we can't just put a 0.5, right? We can't. We have to have some knowledge of what that standard deviation is, kind of like I gave you here. All right, so at the end of the day, now we need to put our algebra skills to test to solve this. First thing I'm going to do is I'm going to divide, or excuse me, the opposite of dividing is to multiply. I'm going to multiply the square root of n to the other side. You cannot square both sides yet because it's only in the denominator. So once I multiply, it cancels that out. Okay, so that is gone. Then I have to divide the 2.4 over. So I'm going to carry my work up here. So I'm going to take the square root of n, and I now have 1.96 times 0.7 divided by the 2.4. Now, since the square root is only on the n, my final step would be to square both sides completely to solve for n. All right, so I'm actually going to go ahead and do this on the calculator. I mean, that was actually pretty easy math. It wasn't too complicated. All right, so let's see here. I'm going to use some parentheses. 1.96 times 0.17 divided by 2.4. And I got to square all that. So notice I'm not rounding anything. I'm typing everything in all at once. And I get a very, very small sample. Now, what does this tell me? Well, I mean, you can't have a sample of 0.019. It doesn't even work out. That doesn't even make sense. What am I going to round that up to 1? So this does happen, right? And all this means is that the parameters I set forth just aren't going to work. They're just not, right? It just doesn't seem to make sense. I did all the math correct, but at the end of the day, I just chose parameters that don't make sense. And I just want you to be aware of, this does happen. I hope that the AP would never give you a problem like this. They're going to give you a problem where it actually works out. So let's do a second version of this that's very similar to this one where it does work out. All right, so here's the exact same problem with a couple changes. And, I really wanted to show you an example that doesn't work out because sometimes that happens and it actually makes you see that the data doesn't always work the way you want it to. So here's another example, same problem. Marcus is trying to find the mean circumference of spherical marbles that his company makes. 95% confidence interval. This time he wants a margin of error of only 0.4 centimeters. Boy, that's a pretty small margin of error. Up 0.4 centimeters, down 0.4. And he wants a 95% confidence interval. And it does say that previous data has a standard deviation of 1.7 centimeters. So slightly different value there as well. And it's just crazy because these slightly small differences are actually going to make this problem make a lot more sense. So again, the margin of error he wants is 0.4. I can't find a T star because I don't even know my sample size. I'm just going to have to revert back to a Z star. The standard deviation that has been shown true in the past is 1.7 divided by the square root of my sample size. Multiply the square root of n over, and then divide by the 0.4. 1.96 times 1.7 divided by 0.4. And then you're going to go ahead and square both sides. Now, this is going to work out to make a lot of sense. All right, so I'm going to have a parenthesis, 1.96 times 1.7 divided by 0.4. Put all that in parentheses and square it, and now all of a sudden I get an answer of 69.38. Always round up, so 70. So if he has a sample of 70 of his marbles, then he could get the margin of error he wants, which is very small, and he can still get that 95% confidence level. So two good problems to look at. It really is important to kind of understand what happened here. And this does happen. It does happen where the numbers just don't make sense. It just doesn't work. So that's why, again, the AP is not going to give you a problem that doesn't work out. But it's important for you to follow the proper procedures to see how it definitely will work here. If the numbers are right, all right, it all makes sense. All right, so let's move on to the final topic in this video. How can we justify a claim? This is perhaps the best part of what a confidence interval can do. All right, this is actually also the easiest part of this entire video. If you're finding anything difficult, this is unbelievably easy. All right, suppose someone or some organization makes a claim about a population mean. For example, let's say the CEO of a name brand battery company makes a statement that the mean amount of time their AAA batteries last is at least 350 minutes. Now, at least means 350 minutes or more. They claim that their batteries last 350 minutes or more. That's what the CEO says. Well, we can actually use a confidence interval based on a sample to either justify their claim as possibly being true or to find out that their claim is unfounded. So let's go back to our confidence interval that we found. Remember, our confidence interval was trying to find the mean length of time that a AAA battery lasts. And remember, our confidence interval was 340 to about 357. So what do you think about the CEO's claim? He claims that his company produces batteries that last at least 350 minutes. Does our interval support that, or does our interval go against that? Well, 350 falls in my interval, so I guess my interval supports his claim. I can't say he's wrong. 350 could certainly be true, and it could even be higher than 350. Now, yes, the truth could also be lower, but if you want to word it like this, I do not have significant evidence that he's wrong. If you try to, I don't want to say that this is a test because there's a lot of different procedures that need to be done for tests. But, he makes a claim that it's more than 350. That's his claim. And I don't have any evidence to say he's wrong. I'm going to go ahead and say that, if anything, I do have evidence that he's right. So you could word it a couple different ways. But, if you look at my interval, there is plenty of evidence that this CEO could be correct. You can't look at the fact that, well, wait a minute, he could be wrong. You're right. But the truth is that I don't know. I don't know what the truth is. So I can't say he's wrong. I can't claim he's wrong. So I'm going to go ahead and support that this CEO is telling the truth because his value does fall within my interval. Let's look at an example where the opposite of that happens. This was our systolic blood pressure problem that we did in the previous video as well. We were trying to find the mean systolic blood pressure of teenage male athletes, and we came up with the interval of about 111 to 117. Now, suppose that a news report claims that if a person's systolic blood pressure is exceeding 120, he or she is at risk for hypertension, which is high blood pressure, which could lead to heart disease. So anything exceeding 120 is kind of like the danger zone. Well, based on my interval, could a teenage male athlete be at risk? Well, no. My interval is all less than 120, so my interval does not support any claim that teenage male athletes should be concerned. Now remember, I'm looking for a mean here. I'm talking about the mean of all teenage athletes. So generically speaking, no, a male teenage athlete should not be overly concerned that they are at risk for hypertension because my interval shows that the truth is somewhere lower than 120, 111 to 117. But does that mean that any one person could be at risk? Well, of course, right? Any one person could be at risk. Any one teenager could have a blood pressure over 120. We're talking about the group as a whole, right? The mean. A blanket statement, teenage male athletes as a group should not be concerned because 120 is not my interval. I'm entirely below it. However, that doesn't mean that any one single kid could not potentially have high blood pressure because that's an individual. We're talking about a mean here. But the idea is a claim has been made. We need to justify or not justify that claim based on our interval. So here, the CEO's claim fell within my interval, so I guess he could be right. I can't say he's wrong. Here, I truly believe that I have evidence that teenage male athletes as a group will not have hypertension on average. All right, so that's pretty easy. That fits directly in line with everything we learned back with proportions as well. So hopefully that all makes sense. And lots of little fine details in this video. Make sure you take the time to kind of understand all of them, and they'll really kind of help you hone in on understanding what a confidence interval is all about.